All right, we have one last thing to do. One quick statement to do with circles. And then we'll move on. The next section is inscribed polygons. So inscribed n-gons and circles where n is bigger than 3. We've just looked at triangles so far. And I'll give it a much shorter treatment than the textbook does. So, in fact, today might be a short class. We'll see how this goes. So one more corollary. And I sort of hate where I'm positioning this because, and it's the same place the textbook does, but I did mean to state it a little bit earlier because it's kind of awkward to state it here. But they write that this is a corollary right after the Pythagorean theorem. And it feels like they're saying this is a corollary of the Pythagorean theorem. It's not. It's a corollary of the main theorem that we had with inscribed angles being half of the arc that they inscribed. So we'll say that it's really not even a corollary, it's just a special case of the main theorem. Which I wish we had given a name when we stated it, but we haven't. So it's just the main theorem of this section. And it says the following. So given triangle ABC, the angle at vertex C is a right angle if and only if side AB is a diameter of the circumcircle. Right, the circle in which this triangle is inscribed. By the way, are you guys familiar with the shorthand notation for if and only if? Yeah, you should be right. So IFF. Usually in statements of theorems, I will write the whole thing, but not always. So IFF is if and only if. If I'm using logical implications, right, this means it applies one way. This means applying the other. If you have both directions, that's also if and only if, or equivalently. So what is this saying? This is saying, all right, let's just draw the circle first. I have I don't want to label this. I will go clockwise. Even though it's B and C. Alright, so here's my inscribed triangle. Right, so it says two things. It says the forward direction is if angle C is a right angle, then AB is a diameter of the circle, right? I believe that's what it's saying, yes. And vice versa, if AB is a diameter, then any inscribed triangle using AB as one of the sides must be a right angle triangle. And I want to prove this just to show you sort of a quick method of proof sometimes with these if and only if statements. So we'll prove the forward direction for starters, right? There's two directions we have to prove. And I'm just going to write down a string of statements that follow logically from each other. So what's our assumption? Our assumption here is angle C is a right angle. So we'll just say, all right, angle C is 90 degrees. And this is going to be my proof. My proof is just going to be a string of these logical implications after each other. So what does that imply? What does that imply about the arc AB? How many degrees is that arc?
180.
Yeah, 180, because it has to be twice this angle, right? AB, this arc AB is inscribed by this angle C, so that arc is 180 degrees. And pretty clearly, you could take this as an alternate definition of diameters if you want. An arc of 180 degrees corresponds to this line AB being a diameter. So pretty obviously that implies that AB is a diameter. So there's the forward proof. If angle C is 90 degrees, then this line segment AB must be a diameter. And what you'll do here is realize that this is all completely reversible, right? If AB is a diameter, then this is always true, then the arc AB must be 180 degrees, so it actually implies the opposite direction too. And if arc AB is 180 degrees, well, this angle here must be half of that, so angle C must be 90 degrees. So this can be read backwards too. This guy implies that angle C is 90 degrees. And then we're done, right? That gives us the backwards direction, just reading this backwards. So in fact, I've proven the whole thing right there, just by reversing the logic. And if you can do that, that always makes these if and only if proofs look a little bit cleaner, because it's really not two separate proofs you have to read, just reverse the steps. And it makes it a very, very short proof. Any questions? Awesome. So I'll assign some homework from this section. And I wanted to just work another problem. So I thought the following might be totally fine for homework, but since we'll do it in class, I won't assign this particular one. And it's number 8. So this is problem 1F, the section we're in, number 8, and it says the following. It says, as shown, so I'll draw a picture, although the picture is not really necessary. As shown, two circles meet at points P and Q and diameters PA and PB are drawn. I suppose actually that's not descriptive enough to not require a picture, so we do need one. PA and PB are drawn. And we want to show that the line AB goes through the point Q. So again, it might not actually in my picture, we'll just force it to, because I'm not drawing perfect circles here. But here's what we have. We've got two circles intersecting at 2 points, P and Q. And I'm just going to draw on any old two diameters, one of each circle. So here's that's not quite a diameter, but pretend it is. There's a PB. And I'll try to make this go through. And here's another diameter of the other circle, PA. The problem is to prove that this line segment here connecting A and B together always passes through Q. So you'll want to use what we know from this section, obviously, right? It's a problem for 1/2. And in fact, the corollary we just stated should prove this one fairly quickly. But I will give you a few minutes to think about this. Think about sort of how you would start. How do you show that Q is on this line? What does that even mean? What are different ways you could do to show something like that? So I'll give you a few minutes before I say anything. Any thoughts on what you might want to show? Like how would you go about proving? What's your strategy here? How do you show that Q lives on this line?
I drew a line from P to Q, and then since PB is a diameter, that means Q is a right angle.
So hold on, what's your strategy for starters? What are you trying to show?
Trying to show that they're two right triangles back to back.
So your goal is to show that this angle here is
180.
180.
Yeah.
So yeah, I think that is probably the best way to go here. Is you want to show that this is a straight line, right? That it doesn't look like A, Q, B. Right? If this is a straight line, then you should be able to show that angle AQB is 180 degrees, right? That should be an equivalent statement to the claim that Q is on this line. So that's sort of the best strategy I could come up with as well, is showing that that must be 180 degrees. And how do we do that? Now we get into the idea you were suggesting, which is let's throw in an extra line here. Let's throw in the line PQ. And so the proof is let's draw in the line segment PQ. By the previous corollary, because PB is a diameter, this angle right here is in fact 90 degrees. Alright, so by the previous corollary, angle, what is that? PQB is 90 degrees. Let me just, I really should have said Y, so because PB is a diameter. Full disclosure, I don't typically tend to think in terms of that corollary. It's an obvious enough generalization for me that, hey, this is 180 degrees, so this must be 90. It's just half of that. But we can invoke the corollary. And completely analogously, so similarly, I'll say this angle on the other side is also 90 degrees, because PA is also a diameter. So PA is also a diameter. So similarly, angle PQA is 90 degrees. And the result follows. Right, we're done at this point. The result follows almost immediately, but I'll state exactly why anyway. Is because AQB is the sum of these two angles, right? The result follows angle AQB is the sum of PQA plus PQB, which is 90 degrees plus 90 degrees, which is 180. And there's some other problems from this section that are as straightforward. There are harder ones with some pretty cool pictures involved. I'll try to assign at least one of those cooler ones, I think. But any questions? So I just wanted to point out that this can be a strategy sometimes, right? If you're trying to show a point that was on a line, we'll show that it's a straight or linear angle, and that confirms that, yeah, this is actually a straight line. So Q must be on this line segment. And with that, we can move on to 1G, which is inscribe polygons and circles. I really think you should have named this section just regular polygons, but anyway. This will be our first definition. So what's a regular polygon? Which I'm sure some of you must know, right? What's a regular polygon?
Isn't it that they have all like equal angles and side lengths?
All equal angles and side lengths, exactly. Right, so it's regular if all its sides are equal. And all its angles. Typically, let me not say typically, but this also means that all the exterior angles are equal. I tend to think of this in terms of interior, really, what do people think of. So all its interior angles are equal. You could say all its angles without confusion because really all the angles are equal. So just for example, here a regular three-gon, regular triangle, that's an equilateral triangle, right? Equilateral triangle, which of course all three sides are the same length and all three angles are 60 degrees. What's a regular four-gon? Square. And if you have all four sides the same length, you're a rhombus. But if you have all four sides the same length and all angles the same, then all the angles must be 90 degrees, You're a rectangular rhombus, so now you're a square. So the first observation is that using circles is really makes constructing regular polygons really quite easy. So we can construct a regular n-gon. And I won't often write this, but when I'm talking about n-gons, I of course always mean n is bigger than or equal to 3. There's no such thing as a polygon with only 2 sides. So when I talk about n-gons, I always mean n is at least as big as 3. It's at least a triangle. By successively marking n equally spaced points, that I'll give names to right now. We call it a sub 1, a sub 2, to a sub n, around a circle. And then drawing the chords that connect adjacent points. Okay. And drawing chords, let's say A1, A2, A2, A3, and so on, AN, A1, between successive points. Successive points. And so here's all I'm saying with this. I won't do an equilateral triangle or a square because that's kind of boring. So I'll try to do a pentagon here. We'll see if it actually looks regular. Probably. Here's A1. Here's A2. Here's A3. A4 and A5. So what do I mean by equally spaced? I mean these arcs between these points all have the same degree measure, right? So hopefully these are 5 equally spaced points, and all we're going to do is draw chords between successive points. So we've got a chord between A1 and A2, chord between A2 and A3, chord between A3 and A4, A4 and A5, A5 and A1. So, does it look particularly regular? My A4 is a little bit off. If I had pulled this a little bit further left, it would have looked better. But anyway. So my claim is that all these chords are the same length, right? I want to verify that this is actually regular. So I need to show all the sides are the same length, and all of these interior angles are the same as well. So, all these chords are the same length. So, why? How do I know they're all the same length? Well, remember, you usually want to work with triangles, right? In geometry, triangles are sort of the most basic object, and I can construct a whole bunch of triangles here just by putting in the center of this circle. So here's center O. And I'm going to draw radii out to each of these points. So I don't know if I want to write down this argument fully, we'll just sort of go through it, we'll just talk about it. But draw radii from O out to each point. This constructs a whole bunch of triangles. What types of triangles are these?
Isosceles.
They're all isosceles, right? All of these radii have the same length. Call the radii r if you want. So this constructs n isosceles triangles. And I'd like to show they're all congruent. Right? If they're all congruent, then they all have the same base lengths, which means all the chords are the same length. How do I know they're congruent? Well, all of those angles must be the same, right? In fact, what is this angle right here?
360
Divide by n, right? Or divide by 5 in this picture. So this constructs n isosceles triangles with the, we'll just call it the peak vertex or something, the peak angle, the angle at the top, the peak angle being 360 degrees divided by n for each of them. This means they're congruent by SAS. By SAS, they are all congruent. They are all congruent. So indeed, every single one of these chords has the same length. And the only other thing we need to argue is that they have the same angles. So all of the interior angles are also equal. Again, I ask you for an argument why.
Since they're all congruent isosceles triangles, all the angles towards the outside are the same.
Yeah, and in fact, we don't. I was going to say we don't even need the fact that it's isosceles, but regardless of that, we'll just brush that under the rug, right? Base angles of isosceles triangles are equal, so all of these, and they're all congruent, so all of those base angles are equal. And the interior angle is just the sum of two of those guys, right? So the interior angles that we've drawn here, they're all the same. They're just the sum of these two base angles. So how do I want to write that? Let's actually let's talk about exactly what that angle is. So, what's a center angle? Center angle, as we observed, is 360 over n. 360 degrees over n. And that means that the base angles of these isosceles triangles, triangles is, what would they be? So together, they would add up to 180 minus this center angle, right? So individually, they should be 180 minus the center angle divided by 2. So this would be 180 minus that center angle all over 2. And this would mean the interior angles of the n-gon are just twice this number. So multiply it by 2, and you have 180 minus 360 over n. And this form is actually kind of ugly. Most people don't write it in this form. How can we make this look better? I believe people factor out 180. And we'll factor out an n, or divided by n. Let's factor out divided by n. What am I left with? I pulled out 180 from this, I've divided by n, so I need to multiply this first term by n. And I pulled out the n from here, so this should just be n minus 2. And I'll just sort of separate this out because there's the formula for the interior angles of an n-gon. You can regular n-gon. You can verify, for starters, this works for triangles and squares, right? Plug in n equals 3, n equals 4. You get 60 degrees and 90 degrees. And what I'd like to do, there's actually a homework problem in the book that sort of asks you to demonstrate something that leads immediately to the claim that what we've shown is we can build regular triangles like this, right? We can build regular triangles by inscribing them in circles like this. The claim is that you can get all regular triangles, or all regular polygons this way, right? So if I have a regular polygon, it is indeed inscribed in some circle. So here's the fact that I might assign for homework. All regular polygons can be built this way, or can be obtained in this way. And the homework problem sort of does this in a very geometric sort of way, dealing with triangles and talking about lines, whatever, geometric type proofs. There's a very sort of easy analytical way to see this, right? Here's one regular pentagon. What's the only difference between all regular pentagons? Only difference between all regular pentagons would be the side lengths of the pentagons, right? And it's not too hard to see that I can get smaller pentagons just by shrinking the radius of the circle. Right? And I can get bigger pentagons just by increasing the radius of the circle. So sort of doing this analytical argument, and the fact that these side lengths would increase continuously, so I'm not jumping over any particular values, it's pretty clear that just by choosing an appropriately sized radius, I can get all regular pentagons of all given side lengths, right? Using sort of a continuity argument there. And there's nothing special about pentagons. You can do this with hexagons, heptagons, and so on. So there's an analytical argument, but there's a nice way to do it geometrically as well, and I think I'll assign that for homework. The last thing I want to do is talk about area. So let's redraw the picture I just destroyed. A1, A2, A3, A4, A5, so let's see. S is going to be the side lengths. So side lengths of regular polygon. Actually, let's call it an n-gon, because we'll need n later on. So this is just the length of these chords, right? So i.e. the chord lengths. So each of these have the same length, and they have length S. And A is going to be the length of an apothem. Anyone know what an apothem is for regular polygons? So I was intrigued when I was reading through the textbook. He spells this with a G. Right after the E, he throws in a G. And I thought, that's strange. Maybe this is some sort of archaic spelling, right? I looked it up. I can't find any reference to it ever spelled with a G anywhere. So I thought he must have just made a typo. But then I looked through the problems, and he does it again. So for whatever reason, the textbook throws an extra G in there. I don't think anyone else does that ever. So what's an apothem? Here's an apothem. Here's the center. So we've got all of our radii. There's our radii. An apothem is just an altitude of one of these triangles, which, since they're isosceles, also means it's a median, also means it's a bisector. So that connects right there to the middle. That length is A. That's an apothem. A for apothem. So this is an altitude, or a median, of the triangle from center O. So I suppose I could be even more precise, right? And most people, when they're talking about apothems of regular polygons, they don't talk about these cutting it into triangles and everything. An apothem is just a length from the center of the polygon to the midpoint of one of the sides. Okay? And R is going to be the radius. So let's talk about areas. Area of one of these isosceles triangles. Area of one isosceles triangle. For example, this isosceles triangle right here. What's the area of this guy?
A times R.
A times R?
Or no, sorry. Yeah.
Not 1/2 R. Remember it's base, right? The base is S. So it's
So it's
1/2 times AS, right? 1/2, in fact, in my notes I've got SA, so we'll go the other way around. 1/2 times the base, which has length S, times the height, the apothem A. So the area of the regular n-gon is what? How many of these triangles do we have? N of them. So it's just n times 1/2 SA. Or rearranging that so it looks a little prettier, 1/2 n SA. So this is where this apothem comes from. This is why people talk about it, because it's a really nice way of expressing the actual area of one of these regular n-gons. And you'll sometimes see this written slightly differently. What's the perimeter? What's the total perimeter of this n-gon? Each side has length S. We have n sides, so n times S, right? N times S, we'll call that the perimeter. So that's 1/2 times PA. Perimeter equals NS. You sometimes see this formula as well. So I promised a short class today, we'll just make one more statement. I will call it a theorem. It is a big theorem, but we'll state it without proof. And it's the following. So let n bigger than or equal to 3 be a fixed integer. Among all possible n-gons inscribed in a given circle All right, so I'm fixing n. When I talk about all possible n-gons, I mean with a fixed n. So maybe all possible pentagons. All right, so we're looking at all possible pentagons you can ever inscribe in a given fixed circle. The regular n-gons are optimal. They're maximal in some sense, and they're maximal in the sense of they contain the most area. So regular n-gons have the largest area. Right, that is, if I wanted to inscribe some other pentagon in this, so maybe I decide instead of going regular, I'm going to move this vertex over here. Right, so I've got this. Here's another inscribed pentagon. That's guaranteed to have less area than my regular pentagon. So regular polygons are nice in the sense that they maximize area of inscribed n-gons. I don't think there's any real good way to prove this geometrically, and the author of the text recognizes that, and he goes with the standard proof that involves lots of analysis, invoking compact sets, and what is it, intermediate value theorem? That's not the word I'm looking for. But lots of results from analysis to demonstrate that yes, there must be a polygon of maximal area, and the polygon of maximal area is regular. But the proof is lengthy. If you want to read it, feel free to read through the text, but I don't think we'll ever really need it, so we won't bother. And we'll end a few minutes early today. Have a wonderful weekend. He also says a few things about pi and algebraic numbers and transcendental numbers and stuff. Again, not something I think we need, but if we do, we'll mention it when the time comes.